This video is on rolling motion and it covers chapter 13-4 of the textbook. Okay, so if you think about an object rolling, like a tire, there's a lot of different motion going on. So there's translational motion as the object rolls along, right? So it translates in space. So you could think about the speed or a velocity of every point, and that's actually going to be the same if you imagine your tire just translating in space. Now you can also think about a rotation, and here it's a rotation about the center of mass. So if you take this pure translation plus the pure rotation, you add those together, you get rolling motion. So now for the rolling motion, it's actually the center of mass that moves at some nice, well-defined velocity v. And each point, though, is actually going to have a slightly different velocity since it's rolling and translating at the same time. Now, the key is if you have an object that rolls without slipping, so then you can relate the angular velocity to the linear velocity. So imagine you have a tire that makes one complete revolution. Well, the translational displacement has to be equal to the circumference of your object. So, and when you do that, that allows you to relate the displacement of the center of mass has to be the angular displacement times the radius r. The velocity of the center of mass has to be the angular velocity times the radius r. And the acceleration of the center of mass has to be the angular acceleration times the radius r. So, and then also the total kinetic energy of the object, like we saw in the last video, is going to be the sum of the linear kinetic energy of the center of mass, 1/2 mv squared, and the rotational kinetic energy around the center of mass, 1/2 I omega squared.